Welcome to July's Leetcode challenge. Today's problem is binary tree level order traversal 2. Given a binary tree, return the bottom-up level order traversal of its nodes' values from left to right, level by level from leaf, bottom leaf, to root. For example, given this binary tree, we want to return a list of lists where each list is going to be the level from left to right of the node's values. 15.7 comes first because that's the most bottom leaf level, and then 920, and then 3 on top, which is the root. There's a couple ways to approach this. Whenever we want to do a full traversal through a binary tree, we could either do a depth-first search or a breadth-first search. And if you recall, a depth-first search goes down the path to the leftward leaf and then recursively calls the rest of the paths, while breadth first goes from level to level. So it starts at 3 and then traverses through the entire level each time. So intuitively, I thought going a breadth first search route would be the most appropriate, but both could work, and I'll show how that can work down the line. So what I'm going to do is do a breadth first search through the binary tree, but the key insight here is we need to keep track of the levels we're on. That way, whenever we find ourselves at a new level, we could append a temporary list into our output and start creating a new temporary list, adding all the values for this level. And once we're at the bottom, once we're out of this breadth first search, we can add that last level. And that's going to actually create a list that goes from top to bottom, but that's fine because we can just return it reversed. So let's begin. Let's start off by going with our breadth first search approach. And in order to do that, usually you want to form a queue. So I'm going to make a queue using the queue. And what I need to do is not only store the node pointer, but also the level that we're on, because this is going to allow us to keep track of when we want to append the list and start a new one. So what I'm going to do is add the root and as well as the level, which I'll start with 0 as the first level. So while there's a queue, what do we want to do? Well, first we want to pop off what's on the queue, right? And what gets popped off? Basically the current node and the level. And I'm going to have to initialize a bunch of other variables in order for this whole thing to work. And I want to start with initializing the output, which is just going to be an empty list, as well as a temp list, which is going to be what's going to be built up for every level, as well as the, let's call it previous level. This is what's going to indicate to us, like, are we on a new level? So should we append our temporary list to our output? Okay. So now that we popped off our node value, the first thing we want to check, okay, well, first we want to see if there is even a node, right? Because what I'm going to do at each point is append the left child and the right child to this queue. So what I'll do is queue append, and I'm going to add a tuple of the node.left, as well as increasing the level by 1, and we'll do that for the right side as well. Now this is the part where the logic kind of gets icky, but first we want to check if there is even a node, because if there's not, we're just going to skip this. And if the level has changed, this is where we want to append our temporary list into our output. So if level does not equal the previous level, then we're going to add our temporary list to our output. We're going to reinitialize our temp to a blank one, and we are going to increase our level, or just make that equal to the current level. Finally, if we need to make sure that we need to add the current node's value into a list, into our temp list. Now, one thing to note is at the very last level, I actually won't be adding this temporary list because it'll just follow the loop. So I need to make sure that if there is a temp list at the last level, we need to add that to our output. So we'll just do the same thing here. Now finally, once that's finished, we can just return our output, but we want to make sure that's reversed. And one way you can do that is like this in Python. And let's make sure that this runs. And okay, it looks good. Let's submit that. Okay, great. So that's accepted. But what I found was the logic, I didn't really love my logic and thought maybe there's a better way to do this. And we could go with a depth first search approach. And the way that we can keep track of what level we're on is actually making like our output, each index in our output, since all those are going to be lists, make that equal to the level that we're currently on. And if we discover that we're on a new level that doesn't exist for this output, we need to make sure to add another list to this output so that we have a list there for that current index number, which represents a level. Okay, so I'm going to write a helper method. We'll call that DFS. And again, we'll still need to pass in the node and the level to keep track of where we are. So it's pretty standard. We're going to start with saying if not node, just return to end our recursion. And basically, we need to pass in our node dot left as well as level +1 and node dot right as well as level +1. Now the key thing here is we need to make sure that our output contains this level, right? Okay, so how can we do that? Well, how about just checking the length of the output and making sure that it's not less than the level given to us. So to do that, just say if the length of the output, so say that we had only nothing in there, so it would be 0, and we need to make sure that we're gonna say enter level 0 here. Yeah, enter 0. We need to make sure that there is a list at that point, right? So I'm gonna add a 1 just because the way that length and indexes work. And if that's the case, then we want to append to our output a list. And this is going to be a list that at the very end, what we'll do is say, hey, for this index level, please append our node value. And that would be it. We just pass in the root and say level 0. And again, just return the output reversed, because keep in mind this is going to still do it from the, like at the end it's going to look like top to bottom, but we want to return a bottom to top. So let's make sure this runs first. And it looks pretty good, so let's submit that. And accept it. Yeah, so this actually is my preferred approach, which surprised me because intuitively I thought breadth first search would be much better. But I suppose that if we're able to store the list as the level, we get that intuition right. We need to store the levels during our traversal, and we could pinpoint the index number as the level. Then it really doesn't matter. Like depth first search would be totally fine, and it does actually look cleaner than my breadth first search approach. So hopefully that'll help you. Thank you.